Hello, ladies and gentlemen. My name is Stephen Berent, and I'm a sophomore at Archbishop Carroll High School. This is my project on the age hardenability of additively manufactured aluminum alloys. Metals are used in all sorts of industries today, such as the aerospace and automobile industries. The goal in these industries for the metal is to have for it to be lightweight with a high durability. I specifically chose aluminum because it is lightweight, and I was interested to see if I'd be able to increase the strength. My question for this experiment is, will the aluminum alloys increase in strength after the age hardening process? My hypothesis was that with longer hold times and higher temperatures, the aluminum alloys will increase in strength. My materials included the aluminum additive samples, the heat treatment furnaces, which I was allowed to use on base at Wright Pat Air Force Base specifically, with the help of other doctors which guided me along the process. Then with also metallography equipment, which includes mounting epoxy, polishers, diamond polish, carbide tapers, microhardness tester, and the microstructure interrogation equipment. Then we also would use optical microscope and a scanning electron microscope for investigation into the microstructure after the project has concluded. The procedure was first to obtain the aluminum additives, which was done on base at a lab. How this works is they basically put the metal as a powder on, and a laser goes over it, which melts it and then rapidly cools so that it has a layer of metal. You do this layer by layer, and you get your structure. This sample, or each of these samples actually, was a cube 1 inch by 1 inch by 1 inch. After we obtained the samples, we would put them in at 2 times, 385 degrees Celsius and 415 degrees Celsius, at times of 10 minutes, 20 minutes, 40 minutes, and 80 minutes. After each sample was taken out, we would quench it in water, freezing the metal in between phases, because as it's in the furnace, the microstructure is changing and it's becoming more of a liquid because of it. But we are not at a high temperature where it's turning into a liquid. The microstructure is just changing, and by quenching it, you freeze it very rapidly wherever it is at. We chose water specifically because it was what they had offhand and ease of access. Because of oil, it is harder, it is more expensive, and they didn't have any available. Then we would mount the samples in the epoxy. We do this with a machine. This machine is shown right here, if you're able to see. How that works is you place the sample on the mount and it lowers it down. You then put the given amount of epoxy onto it, it's epoxy powder, and you then close the machine and it compresses the sample at a very high heat, and then it cools off. This is used so you have something to hold on as you do the grit papers, or you grind it so that it has a mirror finish. Shown right here, you grind the sample onto a paper. This paper is spinning at 200 revolutions a minute, and what happens is that it puts crevices along the sample, and it allows for you to get a smooth surface because it puts crevices facing one way. Then you rotate the sample, have a finer grit paper, and then you have crevices facing a different 90 degrees to the other ones, facing this way. Then you rotate 90 degrees, do the same thing at a finer grit, and you get closer and closer to the being a really smooth surface. Then you finish off with a diamond polish, allowing for a nice mirror finish on the metal. This is used for the indenting process, which a machine does. What happens here is there's a diamond tip, or basically a small diamond pyramid, that applies 10 grams of force to the metal and indents it. It indents it in 10 different spots along each sample. It measures the strength through finding the length, width, and depth, and then using calculation to find that. It calculates the strength of each indent, and then it'll get the average for that one sample, and then it does the each for the rest. This is very nice to have today, because before this machine was invented, we would have to do it manually through finding the length, width, and depth, and then calculating it yourself. This process could take days, hours, weeks, but luckily we have this machine now. Then after that, we would graph the paper and put it on a spreadsheet, and then we examined what the overall grain structure and integrity. We did this through the scanning electron microscope. Sadly, I was not able to obtain any of the pictures. My results are right here on this table. It is shown through the Vickers hardness scale for the strengths. At 385 degrees Celsius for 10 minutes, it is at 137, 20 minutes, 135, 40 minutes, 134, and 80 minutes, 135, showing a decreased slope of 2. This disproves my hypothesis because first, it barely changed and it went down instead of having an increased slope or increased strength. At 415 degrees Celsius, at 10 minutes, again, I had a strength of 137, 20 minutes, a strength of 135, 40 minutes, a strength of 131, and 80 minutes, a strength of 134, disproving my hypothesis again with a decrease of 3. We had a control group in this experiment, which was just polished with the grit papers and such, but had no heat treatment or age hardening time whatsoever, and this had a strength of 134. The graph, right here, shows this data very well, with the blue being the 10 minutes, the orange or red being the 20 minutes, the yellow the 40 minutes, and the green the 80 minutes. This separate blue over here is the control group, and as you can see, the 80-minute time for the 415 degrees Celsius and the control group were the exact same with a strength of 134. This change of 137 to 135 and 134 is relative to nothing because of previous experiments done on magnesium, not by me, by others, show that it goes up, that can go up to about 60, because magnesium started at a strength of about 50 and increased to 110. Again, through the Vickers on the Vickers hardness scale. Some recommendations for this project would be to use non-additively manufactured metals, because through doing it additively manufactured, it changes the microstructure, and I would rather do it through, not rather, but it would allow for more changes if I did it the usual way, or the original way of melting it, the aluminum alloy down, and then putting it into a cast and letting it cool there. This could allow for a more dense microstructure and maybe an increase in the strength. Then another recommendation for a future project, possibly, is to use a longer temperature for higher temperatures and longer hold times. So I would like to go up to about 50 hours and do tests of each hour, because by not allowing the sample to go further than 80 minutes, it may not have developed enough, and with magnesium, it went to 50 hours, and it was shown a very nice curve that went up and then started to decrease again because of the structure changes. I would love to do a continuation project of this next year, possibly on aluminum again with the recommendations, or maybe on a different metal, and I would like to try and figure out why magnesium had such an increase rather than aluminum having such a small decrease. Thank you so much for watching. My name is Stephen Berent. Have a great day.